Hello everyone, welcome back. So this time we're actually going to jump into that fancy number I talked about last time, Avogadro's number. I'm a little bit too big. Let's move me... I'll put myself small. There we go. Okay, Avogadro's number. Now, what is that number? Well, it's 6.022 times 10 to the 23rd. And you're like, whoa, that's a huge number. And why is that the case? Like, where did it come from? How did he figure this out? Well, Avogadro had this question, this really big problem. He was trying to do chemistry, and he was trying to count molecules, and he just kept on losing count. You know, a billion in one, a billion in two. Oh, dang it, I've lost count again. Okay, that's not the real case, but it's all because of chemistry. He was a chemist. He wanted to make sure that he could actually solve these things and understand what's going on. And he had this question. Like, they knew what the mass of a proton was, that nice little positive charge thing in your nucleus. And he said, well, then how many protons would it take to make some easy to measure mass? Because the mass of a proton is tiny. It is so incredibly small. It's on the order of e to the negative 23rd. And hopefully you're seeing a little connection there. And so Avogadro's like, okay, if only, like, I knew how many protons it would take to get to, a gram. Because a gram is something I can measure. A gram is something I can look at and hold and feel. I can't feel a proton, and I definitely can't count them. But I can figure out how much mass I have, and I can do that fairly accurately. And so it turns out that if you have a mole, it's a fancy word for an Avogadro's number of something. If you have a mole of protons, that will have a mass of 1 gram. So if you have 6.022 times 10 to the 23rd protons, they will have a mass of 1 gram. And just for this class, that's not technically the case. We usually say that the mass of a proton and the mass of a neutron are the same. It's not 100% the case. They're, roughly equivalent. But the mass of a neutron is actually equal to the mass of a proton plus the mass of an electron. Electron mass is just really, really small. So in the end, it's more or less the same thing. Okay, so why do you care about this? You're like, okay, so there's something called a mole. It's 6.022 times 10 to the 23rd of something. Why is this important? Well, first off, let's remember, moles aren't just about atoms and molecules. You can have a mole of anything. It's a terrifying thing to think about, but like you could have a mole of baseball cards. You could have a mole of suns, which I don't think there are actually that many suns in the universe. You could have a mole of ants. That's terrifying. But a mole is just a number, and it's 6.022 times 10 to the 23rd. Now, why do we need to know this? Well, that works for protons, but what if I want to go from, I don't know, oxygen to mass? Like, how many moles of oxygen do I need to get 40 grams of oxygen? Or if I have 40 grams of oxygen, how many oxygen atoms are there? Well, we use this equation up here. And this was developed by Avogadro in a way because he's the one who started this. And what it says is that the mass that you have is equal to something called the molecular weight times the number of moles you have of that. And just to work out units, that would be gram is equal to grams per mole. That's the units of molecular weight times moles. So you can see that in the end I'll have grams and grams. Okay, so mass is equal to molecular weight times the number of moles. Now, next time I'll show you where molecular weight is on a periodic table. I want to talk to you about that right now. Okay, think about it for this way. Hydrogen. Hydrogen is just 1 proton, 1 electron. Okay, so if I had a mole of hydrogen, and I just told you that it's more or less just a proton, how much would that weigh? Or sorry, how much mass would that have? The answer is 1 gram. So there's 1 gram per mole. Grams per mole is molecular weight. If we go up to helium, helium has 2 protons, okay, 2 protons, and 2 neutrons. Okay, now we've said more or less that protons and neutrons have the same mass. So if I have a mole of helium, and each of those moles of helium has 2 protons and 2 neutrons per atom, well, that's 4 atomic mass units. So what do you think the molecular weight of helium is? Well, that's the mass of 4 protons per atom. So the molecular weight of helium, wonderful handwriting, would be equal to 4 grams per mole. And we can keep on going up. Now, here's the issue. This works great for the first few first few atoms. However, eventually it breaks down because not all atoms have the same number of neutrons. In fact, you very rarely will see something that you don't see 1 or 2 as the molecular weight of any atoms. You'll see like 2.006. But we'll talk about that more next time. For now, remember, the mass that you're holding is equal to the molecular weight of whatever the substance is times the number of moles. So if you know the number of moles, you can get the mass. If you know the mass, you can get the number of moles. And you calculate the molecular weight by looking at its chemical formula. Okay, so that's all for this time. Remember, a mole is just a number. It's a certain number of whatever. It can be anything. And we call it Avogadro's number. Now, I hope this helps you, and I'll see you all next time. Bye-bye.